All right, Lab 3 begins with a little computation of dB from pressure exercise. Our dB equation that we're going to use is constant 20 times the logarithm of the pressure for this first question, 65, divided by 20, another constant, which is our reference pressure of 20 micropascals. Use my handy dandy calculator. I got 65 divided by 20. That's 3.25. Then I need to take the logarithm of that, and for a Windows computer, I have to switch from a standard to a scientific calculator, so you may have to poke around a little bit to find something that'll do logarithms for you. Take the logarithm of that, and I get 0.51. And then multiply that result by that 20 constant. And I get something around 10.2, depending a little bit on whether you kind of round and retype in or whether you keep using the same numbers throughout in the calculator. If my pressure is 700, same equation, 20 log of 700 over 20. So start from the inside, at least with this kind of calculator again. 700 divided by 20 gets me 35. Take a logarithm of that, I get 1.54, and multiply that by 20, and I get 30.88. So I'll go with 30.9, round it to one decimal place. And then last but not least, if I jump up to 80,000, like I talked about in class, I'm taking big jumps in pressure. But when I turn them into dB, they become not quite such crazy jumps. I have 80,000 divided by 20. Take the logarithm of that, 3.6, multiply that by 20, and I get 72.0 if I keep it at one decimal place. Alright, so relatively straightforward, and any sort of pressure dB calculation is always going to be in this direction. We are not going to go the other direction. We certainly could, but it just adds more maybe unnecessary math. Big picture idea is, pressures take jumps by more than 10 times, more than 100 times. dB, however, goes from 10 to 30 to 70, so keeps it within kind of a regular scale without so many zeros running around. All right, for tube resonances, we have two different issues that we have to keep in mind. One is we have different equations for a closed tube compared to a half open tube. And the other, which is actually kind of split across questions 2 and 3, is which resonance am I looking at? Am I looking at the lowest resonance, the second lowest resonance, or technically we could be looking at higher resonances, but we don't use those too much in the analysis of speech, so we'll only talk about higher resonances a little bit. For example, everything we need to do with vowels, which is a pretty important concept, the acoustics of vowels that we'll talk about. The first two resonances give us what we need. All right, so my equation basically has to do with a sound of the right wavelength so that it bounces around in that tube, creates a standing wave that reinforces itself and gets louder, so that that would be one of the sound frequencies that would emerge from that tube, much like blowing into a musical instrument produces particular notes. So we have speed of sound for a closed tube divided by 2 times the length of the tube, in this case 18. I'm going to be bold and say 2 times 18 is 36 without getting the calculator, and then jump to 34,400, my speed of sound in centimeters per second, divided by those 36 centimeters of sound traveling down the tube and back, gives me 956 hertz if I round to the nearest hertz. All right, in the second question, I'm dealing with a half-open tube. So the correct wavelength is from a slightly different wave, because when you hit that open end, there's a weird pressure polarity inverting reflection that happens. See the lecture stuff on that, so that we have to let this sound travel up and down the tube 4 times before we want to add more energy, inject more positive pressure, create reinforcement that gives us a standing wave. For a 10 centimeter tube then, plugging in 10 for my tube length, 4 times 10 is 40, so 34,400 speed of sound divided by that 40 distance it's got to travel up and down the tube 4 times before I add more positive pressure, before I come back to the beginning of my cycle. I get 860 hertz. Okay, same deal. 13 centimeter tube, closed, so I want 34,400 divided by 2 times the length of the tube, because that's closed. So 34,400 divided by 26, though actually you can divide by 2 and then divide again by 13, and you get the right answer. So 1323 hertz. Notice between A and C, I go from an 18 centimeter tube to a 13 centimeter tube. My resonance goes from 956 up to 1323. So the smaller my tube gets, the higher frequency standing waves I get out of that tube. Fits our generalization that small stuff generally makes higher frequencies like squeaky mice. Big stuff makes lower frequencies like trumpeting elephants. Okay, and then 16 centimeter half open tube, 34,400 over 4 times the length of the tube because it's half open, 16. So 34,400 can divide by 4 and then divide by 16, and that works, and I get 538 if I round to the nearest hertz. And again, I went from a shorter tube in question B to a longer tube in question D, and again the frequency drops. So that all makes sense, that all reaffirms that I'm doing things right. Okay, in question 3, we have some of the same tubes and some different tubes, and we're looking at the second lowest resonance. So because of that, we have an additional constant out in front of our equations. So this is second resonance. If you're dealing with a closed tube, in the closed tube situation, we start with our lowest resonance, and then every multiple of that lowest resonance is actually going to work well, is going to echo well in that tube, is going to create a standing wave as well. So we'd get a whole bunch of different frequencies that would potentially create standing waves and resonate well in that tube. All right, if I have an 18 centimeter tube, again, I have that constant of 2 because things are closed, which is going to be different from my constant here where things are half open. So I got a couple of different things I got to worry about in terms of constants depending on what I'm doing. All right, 2 times 18 to fill this out correctly is 36. 34,400. 34400 divided by 36 gives me 956. Had that somewhere before. 956. And then multiply that by 2 for the second resonance. And I get 1911. Oops. Notice if you took 2 times 956, you'd get 1912. So depending on whether you keep all that decimal information in your calculator or not, your answer might be slightly different. On a quiz, you're not going to have 1911 and 1912 as answers. You would have 1911 or maybe 12 plus things that are not very close to 1911 or 12. All right, second lowest resonance again, half open tube in this case. Because it's a half open tube, I have my one constant of 4 because my wave needs to go up and back 4 times in that tube, travel the length of the tube 4 times to resonate well. And then for the second resonance of an open tube, only the odd number multiples of the lowest resonance are going to work. So the second lowest is going to be 3 times. Third lowest, if we do it, is going to be 5 times. Okay, so again, I have an 18 centimeter tube. 4 times 18 is going to give me 72, but let me just double check. 4 times 18 is indeed 72. So now I'm going to take 34400, my speed of sound, divide it by 72, and I get 478 if I round off, which is, for writing it down, kind of have to. Multiply that now by 3, the odd multiple for the second resonance because it's a half open tube, and I get 1433. Or so. If you used 478 directly, I think it'd be 1434. All right, second resonance for a 10 centimeter tube, that's going to be, closed. That's going to be 2 times 34400 divided by 2 times the length of the tube, which is 10. So 2 in front for second resonance of closed tube, 2 inside the equation because it's a closed tube. So we can do 34400 divided by 2 and divided by 10 and get 1720, and then multiply that by 2 and we get 34400. Fairly high frequency, but we got a fairly short tube here. If we were talking about simulated vocal tract, that would be like for a kid at 10 centimeters. All right, second lowest resonance, half open tube, tube length 20 centimeters. Since it's half open, second lowest resonance is an odd multiple. 34400, my speed of sound is a constant. And then again, half open tube, so it's 4 times the length of the tube. I should use a dot, actually, it's a little cleaner, which is 20 in this case. So 34400 divided by 4, half open tube, divided by 20, length of the tube, multiplied by 3, because it's the second resonance of a half open tube, where the odd multiples are resonances, gives me 1290. Okay, so that takes care of the dB and tube resonances. The other spectrogram-related parts of this lab are covered in a second video, so it doesn't get crazy long.